In this section, we're still working with series and infinite series to be specific, but we're looking at some particular tests. We're looking at a test called the Divergence Test, and just as its name implies, it is only a test for divergence of a series. We're also going to be looking at the integral test, so that way we can get back into some integration techniques, and then also a p-series test. So this should be the integral test and a p-series test. So these are the three tests that we're going to be looking at. We'll go through these one by one and then we'll look at a lot of specific examples. Let's go ahead and start with the divergence test. A quick note on the divergence test: the only thing that you can conclude from the divergence test is divergence. You can't conclude convergence. So the divergence test, as it says, is only good for testing for a series divergence. And basically what it says is if you take the limit of the series as k approaches infinity, or whatever your indice is, and you get a limit that's not equal to 0, then the series diverges. So that's pretty simple. You take the limit. If the limit does not equal 0, it diverges. Now, a special note here: only tests for divergence. So the only conclusion that we can draw here is divergence or I don't know. And you might say, well, wait a minute, if it doesn't diverge, it must converge. But it can be inconclusive, meaning it could diverge, but the test isn't catching it. So only tests for divergence. So the only two conclusions here are diverge or inconclusive. And of course, if it's inconclusive, we need to use some other test as well with that. So we're going to go through each of the tests here, and then after we go through each of the tests, we'll look at examples. The next one I want to look at is a p-series test. A p-series has a specific form, k equal 1 to infinity of 1 over k to the p. Now k, if you notice here, is changing. P is some constant. Now if we have different values of p, this series will converge for p greater than 1, and it will diverge for p less than or equal to 1. So that's the p-series test. Now there's a special case of this test, and specifically it's the series 1 over k, and this is an implied 1. So if p is 1, this diverges, but this is called a divergent harmonic p-series. And it comes up quite a bit when we're using some other tests that we'll learn further on in the sections, when we're using some comparison tests. So this divergent harmonic p-series is an important one to know. Now these indices for the p-series test starts at 1, but if this started at 10 or 100 and went to infinity, the same result would occur whether the p-value was greater than 1 or less than or equal to 1. So the indice doesn't end up being terribly important for that p-series as long as it's going off toward infinity. That's kind of the important key point there. The last one we're going to look at is the integral test. Now the integral test has some criteria that must be met before we can actually apply the test. So there's some criteria. So the criteria basically is the function that we're looking at has to be continuous, positive, and decreasing. So let's suppose, s with the p hanging from it is suppose. So suppose we have a function and it is continuous, positive, and decreasing. Now we need to show each of these things before we can actually perform the integral test, and so that will always be important that these are established. Now these will only be true for greater than or equal to 1 values, and then what we'll do is we'll let our series a sub k, and again this is the function that produces that series, equals a real number series, let's say f of k. So again, we're taking it from the integer values to a continuous function for these values of k equal 1, 2, 3, etc., these integer values. Then what we can say is if the series a of k and the integral from 1 to infinity of f of x dx will either both converge or both diverge. So what we do is we basically integrate the series, and if the series converges, so does, or sorry, if the integral converges, so does the series, and if the integral diverges, so does the series. So they either both converge or both diverge. However, if they converge, one thing you want to watch out for is the value of the integral is not equal to the value of the series. We just know it converges. It doesn't tell us what it converges to necessarily. So those are the three tests that we're going to be looking at in this section. And so what we'll do is we'll just start running through and doing lots of different problems and looking at some different setups and kind of the work that needs to be shown for these. So when I run through these, the first thing I do is I look at a problem and I try to see, okay, is it something simple? Is it a geometric series where I can just look at that common ratio? This one is not a geometric series. However, when I look at this, I think I could take the limit of this pretty easy, and that's the divergence test. Because on the exam, I won't necessarily say which test you're using. You'll have to choose the test. So if you can take the limit real quick, that's a nice one to do. So the divergence test says take the limit as n approaches infinity, and of course this is going from an integer to a real value function. Okay, we get that connection from one of our previous sections, and this limit is equal to 1/3. Now we need to say why, and it equals 1/3 because the degree in the numerator equals the degree in the denominator. Remember those shortcut rules that we learned probably back in, college algebra, Calc 1, a little bit in Calc 2 as well. So the degree in the numerator equals the degree in the denominator. This does not equal 0, therefore the series n equals 0 to infinity, n over 3n plus 1 diverges. So if you can take a quick limit and get a conclusion, that's probably the best route to go. You don't need to make it any more difficult than that. Let's go ahead and look at another one. Let's look at n equals 0 to infinity, and let's look at 8n squared plus 1. Now, I'm going to use a divergence test on this. Because I think I can take the limit of this pretty easy. So let's go ahead and take the limit as n approaches infinity. And this equals 0. And of course, I need to say why, and that's because the degree in the numerator is less than the degree in the denominator. Now, if you don't remember these shortcut rules, you would divide through by the highest power of the exponent in the denominator to establish that limit. Now, the divergence test needs this to not equal 0. So the divergence test fails. Therefore, the divergence test is inconclusive. And I have to try some other test. Okay, so what other test could I try? Well, it looks like to me I could try the integral test because I think I can integrate this. So let's look at the integral test. So for the integral test, I have to establish three things. I have to establish that it's continuous, that it's positive, and that it's decreasing. And I can't just say these are true. I have to actually show that they're true. So first of all, something is continuous, something is continuous if basically the denominator doesn't equal 0. So what we can say here for continuous is that it is continuous because 8n squared plus 1 does not equal 0. And we're only looking at these values from 0 to infinity. Now, for the integral test, we usually look at this starting at 1, but that change in the indice doesn't make a huge difference. So again, we can just focus on that 1. Now, it is positive because as I plug in values from a 1, again, we're going to start this off with 1. I should write that down here. It'll have the same behavior. So this indice is changed. It'll be positive because when I plug my values from 1 to infinity in the numerator, I'll get a positive. And then I plug in my values from 1 to infinity in the denominator, it is also going to be a positive. So a positive over a positive is a positive, so that's established as well. Now it also is decreasing. This is a little bit harder to talk about, but basically the way I look at this is they're both increasing, but the denominator is increasing faster. So the numerator is increasing, but the denominator is increasing a lot faster because I'm squaring it. So what happens is this overall fraction continues to decrease. And you could write that out explanation-wise, or you could show that the numerator is increasing, the denominator is increasing faster, therefore the overall fraction is decreasing. Okay, so then what we can do is we can actually integrate this. So we'll integrate from 1 to infinity of x, we'll change these to our real values, over 8x squared plus 1 dx. Now we have to remember integration techniques. This will be fun because we can use any integration technique here. We can use the Powell rule, use substitution, change your variable, integration by parts, trig sub, trig integrals, very, very exciting stuff. So we can use any of those techniques that we've learned here. So u is 8x squared plus 1, du is 16x dx. So using compensation, I'd multiply by a 16 on the inside, compensate with the 1/16 on the outside, and this will look like 1/16 integral of 1 over u du. This integrates into 1/16 natural log absolute value of u, which is 8x squared plus 1. Now if I evaluate this from 1 to infinity, I'm really looking at this in terms of a limit. Now remember, we can't plug infinity directly in. We need to talk about this in terms of a limit. So the way that we'll want to look at this then is we will take this from 1 to a, and then we look at this as the limit as a approaches infinity. So we have 1/16 natural log of 8a squared plus 1. So that's my upper, and then I have minus my lower. Let's see if I can squeeze it in here. I bet I can't. So if I plug 1 in here, I'd have 8. 1 squared is 1, 1 times 8 is 8, 8 plus 1 is 9. So as we're integrating this, and I take the limit then as a approaches infinity, this is the natural log. What's going on with the natural log as the argument of the log goes toward infinity? Well, the whole thing is going toward infinity. So I have 1/16 infinity minus 1/16 natural log of 9 is still infinity. So therefore this diverges. Okay, so now let's go ahead and draw the next conclusion. So the conclusion that we can draw here, and we kind of have to tie this together, we just can't stop with diverge then, is we need to say if the integral from 1 to infinity of x over 8x squared plus 1 dx diverges, so does the series. N equals 0 to infinity. Again, that change of indice won't matter because 0, n equals 0, just produce the value of 0 for our first term. And this was n over 8n squared plus 1. So if the integral diverges, so does the series. And so that's the conclusion that we can draw from there. So that's pretty interesting. If you come back up here, you might say, well, wait a minute. The divergence test up here didn't say diverge, but it diverged. But what the divergence test does is it checks for easy divergence, meaning it catches the things that are obviously divergent. This said inconclusive. Now, inconclusive can mean two things. Inconclusive can be converge or diverge still. We have to just check further. So I guess that's a note that we could make up here, is we could come up here and say, okay, the divergence, oh, I should have the word test here. The divergence test is inconclusive, and this means to do more work or do more tests to figure out what's going on. And the test we decided to use was the integral test. So that was pretty neat. We got to use two different tests. One failed, but again, it's not failing, I guess. It just is saying it's inconclusive, so I need to figure out another way to check to see what's happening with this particular series. Now remember, with the integral test, it's possible that I can use any of the integration techniques that I previously learned. So let's go ahead and look at a series. Let's look at this series from n equals 0 to infinity. And let's look at 1 over x squared plus 4. Actually, we'll do n squared. We have to make sure these are integers, n squared plus 4. Now, I could do a divergence test here real quick in my head, and I can see that this goes to 0. And because this limit as n approaches infinity equals 0, the divergence test is inconclusive. And because it's inconclusive, that means we have to try more tests. So I think that we should be able to integrate this. So I'm going to try the integral test. Now remember, with the integral test, I have to establish three things first. You can't just automatically assume that these are true. We have to show that this is continuous, that this is positive, and that this is decreasing. It is continuous because the denominator n squared plus 4 never equals 0. It is positive because the numerator is always 1, so I have a positive 1. And the denominator, no matter what I plug in here, I square it, and I add 4 will be positive as well. And then it's decreasing because I have a fixed numerator, and I have a denominator that's increasing, which makes the overall fraction decreasing. So what we'll do is we'll just go ahead and integrate this from 0 to infinity, 1 over x squared plus 4 dx. Now this fits a form. This is exciting. This fits the form of 1 over a squared plus u squared. You could do a trig sub on this, or you could recognize that this fits the form 1 over a inverse tangent of u over a. So if we recognize that it fits the form, a is equal to 4. Actually, a is not. A is equal to 2, because that would be 2 squared. U is equal to x, du is dx. So this integrates into 1 over a inverse tangent of u over a. Now I'm evaluating this from 0 to infinity, but I take the limit as a approaches infinity because it has to be in limit notation. I can't just plug infinity directly in. So let's go ahead and evaluate this then. This would be the limit as a approaches infinity of 1 over 2 inverse tangent a over 2 for my upper. And then for my lower, it would be minus 1/2 inverse tangent of 0 over 2. So we have two things that we're looking at here. For this first one, this is saying what angle. So what angle is approached, and you can just say what angle is as well, in the interval negative to positive pi over 2 as, so what angle is approached in the interval negative to positive pi over 2 as inverse tangent, or as tangent approaches infinity. And so if we think about the tangent curve, we can see that this is approaching infinity as this approaches pi over 2. So pi over 2 is my solution here. And this one over here would be what angle, this one's a little bit easier, in the interval negative to positive pi over 2 has a tangent of 0. And the answer is 0. What angle has a tangent of 0? 0 does. So plugging in, we basically get 1/2 pi over 2, which is pi over 4. Now that's not my answer. What this implies is the integral converges. Okay, so now let's go ahead and draw a conclusion, because what we're trying to draw a conclusion about is the series. So therefore, the integral from 0 to infinity, and again, testing this, here we are starting at 0 to infinity. If we look at our term of 0, if we plug a 0 in here, this would be 1/4 for my first term, so it's not a big deal that we are starting this at 0, but I guess technically we could have looked at this as 1, and then we would have said what angle has a tangent of 1, and that would have been pi over 4. It still would have converged. So if the integral 1 over x squared plus 4 dx converges, so does the series n equals 0 to infinity 1 over n squared plus 4. Now it doesn't converge to pi over 4. We don't know that. It just says that it converges. That's all that we know, and that's all that we can say. So we've looked at that divergence test. It's pretty handy. It's easy to do. And we've also looked at the integral test. And the cool thing about the integral test is I have all those nice integration techniques that we've learned that we can still keep using. So make sure that you still are aware how to do like the integration by parts, the trig sub, the trig integrals. I'm trying to think, oh, partial fractions, that's a good one. Partial fractions, any of those that we can use here with the integral test, as long as the integral is continuous, positive, and decreasing. And that has to be established before we can actually do the integral. Let's go ahead and look at some more examples. And now again, we have a lot of these tests. So when we look at these tests, we can kind of run through them. You know, if it's a geometric series, that's easy to pull, or if it's a divergence test, an integral test, or in this case, let's look at the series n equal 1 to infinity of 2 over the square root of n. Now if I wanted to, I could do a quick divergence test on this. And on the handwritten homework or on an exam, if you do a test and it fails, still leave the work there. So we take the limit as n approaches infinity, and of course this is an integer value function, but we're thinking about this as x goes toward infinity of 2 over root x. This is equal to 0. Therefore, and we need to say why, I guess, because the degree in the numerator is less than the degree in the denominator. I wonder if I forgot to say that up here. Yeah, yep. So up here I should have had a reason. The degree in the numerator is less than the degree in the denominator. So come back down here. Therefore, the divergence test is inconclusive. And I think I could probably integrate this pretty easily, but I have to show, with the integral test, I have to show continuous, positive, and decreasing, which this is, but it's a lot of work. So I have to do more testing. So I think this looks like a p-series. So let's go ahead and look at the p-series test on this one. I think it will save us some time over the integral test if it works. So with the p-series test, I want to rewrite this n equal 1 to infinity of 2 over n to the 1/2. So this looks exactly like a p-series with p equal to a half. Now let's go ahead and run back up to the top here. For the p-series test, it will diverge for p less than or equal to 1 and converge for p greater than 1. So we have the case of less than or equal to 1 here. So we have this is less than or equal to 1, therefore this will diverge. That's how quick this is. Now I could have used the integral test on it as well, and there's nothing wrong with doing that, but the p-series test is a little bit faster. Now once again we kind of have that interesting conversation. How come the divergence test didn't say diverge when we find out from the p-series test that it did diverge? And the answer to that is the divergence test only kind of catches the low-hanging fruit, the easy divergence series. It doesn't catch the ones that are a little bit more complicated. So yes, it still diverges even though the divergence test was inconclusive. So that's an example of the p-series test. Now the p-series is kind of interesting. You can use it for a lot more than just a simple p-series like we have here. For instance, we could look at something like k equals 10 to infinity. Notice I'm not starting at 0 or 1 here. And we could look at 1 over k minus 4 quantity squared. Now if we look at this, I can look at this in terms of rewriting this and thinking about a p-series. Now it doesn't quite look like a p-series because it's the k minus 4 that's quantity squared. So the way I think about these is I think about them in terms of expansion of that denominator. So if I expand this, and this is just a quick rewrite, and just as a quick note, I could use a divergence test on this. It would be inconclusive. I could integrate this as well, and I just have to show continuous, positive, decreasing, all of those good things before I could integrate it. But I want to look at this in terms of the p-series test. And it doesn't matter that I'm starting here at 10. If it converges from 0 to infinity or 1 to infinity, it will also converge or diverge from 10 to infinity as well. So I look at this as k squared minus 8k plus 16. So we can't separate the denominator, but I'm going to look at this piece right here. I'm not going to split it out and write this separately. I'm just looking at this, and I look at this and I think, oh, this is a p-series with p equal to 2, which is greater than 1. So p is greater than 1. Therefore, for this particular case, it will converge. So the important things we need to make sure you do here is we always name the test. So I've named it the p-series test. I show the criteria for the test. I find my value of p. I show how I test it. Is it greater than 1 or is it less than or equal to 1? And then I draw my conclusion. So those things all need to be there in order for you to get your full credit. Always name the test. It's really important. And we're going to learn more tests, and you might say, well, there's only a few tests. Why do I have to name it? Because there's going to be a lot of them. And some of them start out in a similar fashion, and then kind of like halfway through, the test changes. So it's important to know which test you're using so you can kind of work through this. Let's look at another example. Let's look at k equal 1 to infinity. For k equal 1 to infinity of 7 over 28 to the k, this is not a p-series. It kind of looks like it could be a p-series, but with a p-series, what ends up happening is it's the base that changes and then the exponent is fixed. So this is not a p-series. What this is, and I think this is a pretty easy rewrite. This should look familiar. Pull this 7 out front, and this would be 1 over 28 quantity to the k. So with a quick little rewrite, this is a geometric series. So again, name the test. It's a geometric series. And with the geometric series, what I care about is this value for r. So r is equal to 1 over 28. So the absolute value of 1 over 28 is definitely less than 1, therefore this converges. Okay, so now if we want to know what it converges to, that's a little bit different matter here. So let's figure out what this converges to. If you'll recall, this converges to a over 1 minus r if this starts from 1 to infinity. But because this is starting at k equal 1 to infinity, I have to rewrite this just a bit. So this is going to be the series k equals 0 to infinity minus basically k equals 0. This is just a k equals 0 case, so I guess it goes from 0 to 0. I don't really know if I like that notation, but you kind of get the idea of what we mean here. So this piece converges to a over 1 minus r. This piece right here, if I plug in k equals 0, I get 7 times 1 over 28 to the 0. So a is 7. 1 minus 1 over 28 minus 1 over 128 to the 0 is 1, so this is minus 7. So let's go ahead and simplify. So 28 minus 1 is 27 over 28 minus 7. So I have 7 times 28 over 7, 28 over 27 minus 7. Whoops, we won't be able to quite fit it on a page, but let's keep working at it. So when we multiply, we have 7 times 28 minus 7 times 27 to find that common denominator all over 27. So I look at this and it looks like to me, I'm not very good with my big numbers here with math, but I see a common factor of 7. So if I factor out a 7, I'm left with 28 minus 27 all over 27. 28 minus 27 is 1. 1 times 7 is 7. So I'm left with 7 over 27. So it converges to 7 over 27. So remember, you have to remember that rule with the geometric series. 0 to infinity is that a over 1 minus r. For any other partial geometric sum, I need to make sure I subtract out that case. That was fun to go look back at the geometric series. Now a lot of times you can rewrite geometric series, and I can look at sums and differences of geometric series. So those are important to look at as well. I think we've covered pretty much everything for the series test. There's some specific kind of some true-false questions that you'll run across in your lecture. So I want to go over those real quick because they might not be real obvious to you. Let's go ahead and look at some examples. For instance, if k equal 1 to infinity, a sub k converges. So if we have some series converges, then, and what we're trying to do is say true false about all of these, what happens to the series that starts at 10 and goes to infinity? So again, we want true or false, and we already saw from one of our examples that we worked through that this is true. So if we have another series, let's say k equal 1 to infinity, a sub k is my series. If it diverges, then what would happen if we had the same k equal 10 to infinity, a sub k? Does it diverge as well? So again, we're looking for a true or a false here, and this one is true as well. So the indice doesn't end up mattering when we're talking about the convergence or divergence. Let's look at another one. If we have some series a sub k and it converges, we don't know how it converges, but it does converge, then what happens if we have the same series, but it's not just a sub k, it's a sub k plus some value here. So I'm going to put plus some number. And would this converge as well? Looking for a true or false. And this would be a false, because I'm looking at the series and I'm summing this number, whatever it is, and so whatever the series is doing, this does not guarantee, because I'm adding this constant to every single summation, that if this converges, this will converge as well. Depending on what this number is, it could diverge, and so I'd have to run through the test to make sure. So this is false. It could be true, but it's a false statement overall unless we know some more information about what that number is. What if we had something like a p to the k? So again, we're looking at my series here is a p to a k. So it's diverging, meaning these values are getting larger and larger. Then if we had some other series, p plus some number to the k, does it diverge as well? And this would be for some sort of a fixed constant. And the same type of thing, we don't know. We can't guarantee that. So we need to make sure that when we look at that, we know a little bit more information. So we can't go directly after, whether that's true or false right away. Okay, let's go ahead and look at another one. Again, these are a little bit tricky, so I want to make sure that these are spelled out for you. K to the negative p, so remember that's 1 over k to the p. So if we knew that this converged, then what would happen if we had the same problem, but in my next exponent I had a negative p plus some number? Does it converge as well? And the answer is false. I can't guarantee that that happens. We don't have any rules saying that. And this one should be familiar. The limit as k approaches infinity of a sub k. So basically I'm doing the divergence test here. Then, wait, actually we need to know what that limit is. If this equals 0, then what are we saying about that series? Does it converge? And this is a big old false. And this is the divergence test. And remember, the divergence test is inconclusive if that limit is 0. So this is just a quick overview of some of those that you'll run across in your lecture that can kind of get a little bit complicated in your My Math Lab homework. So make sure that you look through those. And they're interesting to know, these trues and falses on these, but I think more interesting is actually running through the test. So what are the tests graded on? Okay, so make sure you always name the test that you're working with. Rewrite if you need to. State the criteria for the test, meaning if you have to find R or P or some other value. Do the comparison or the integration or whatever the test is. So perform the test and then draw your conclusion. So it's important that you get all of these pieces in and put together. And I should see this on every single problem when we're working with these sequences and series. As usual, if you have questions, let me know. I'm happy to help. You can send me a screenshot of your problems. You can also set up a time to work with online office hours. Any of those options work for me. And then you also have your Pearson Connect available 24/7 as well online. Enjoy these. These are kind of fun, especially the integral parts. Make sure you kind of dig up your old integration techniques to remind yourself on how to integrate some of those more complicated ones.